In this video, I want to provide a brief introduction to fundamentals of digital logic, some of the reasoning behind including this course in your degree map, and also I will go over some very basic concepts that you need to know in order to be successful in this course. So as for the reasoning, I think it is no surprise for anybody that microprocessors have revolutionized our world. So from cell phones to internet to rapid advances in medicine, you see vast use cases of microprocessors. So the semiconductor industry has grown from a $21 billion industry in 1985 to $300 billion in 2011. And right now it is several trillion dollars. So applications of this industry is widespread across all fields. So it is only natural to learn how computers basically are made. Because if we understand how computers are made, we can design systems that can be used for new applications. So the main purposes of the course is to first understand what's under the hood of a computer. We want to learn the principles of digital design, learn how to systematically debug complex design, and finally design and build a microprocessor. So even though we don't go far enough to design a microprocessor, for those of you who pursue this course and this field further, you will use the concept that will be introduced in this course extensively in designing microprocessors. So now that we have this, we need to talk about some very basic concepts. So the first concept that I'm going to talk about is the concept of abstraction. Then I talk about the discipline, and then the three Y's: hierarchy, modularity, and regularity. So when it comes to abstraction, the definition is hiding details when they are not important. So if we want to talk about all the branches of science that are involved in making a computer, we can start at the very bottom in physics, talk about how electrons interact with each other or with the atoms of a material. If we come up a level, we get to transistors, diodes, more specifically electronic devices. Then from these we can have analog circuits, amplifiers, filters, etc. And then we get to the territory of what we need in this course. Basically digital circuits, basic logic gates like AND gates, NOT gates, OR gates. Combining these basic elements, we get to logic circuits in general. Some examples include adders, memories. And then from these we can go to microarchitecture like data paths, controllers, and then architecture that is basically what we call as a microprocessor. And then on top of that we can have the operating systems and the application software. So as you can see, there are many branches of science that are involved in creating a computer. And these ones are only concerning the computing part, you might say. If we want to be wider or talk more generally, so we definitely need to talk about the power systems as well, right? But for the purpose of this course, we will be only focusing on the highlighted part of this graph. So that means that we don't cover the details that are not important for us. So that is the definition of abstraction. What about the discipline? So discipline means that we intentionally restrict the design choices that we make. So for example, for the designing of digital circuits, we use discrete voltages instead of continuous values. So in general, variables, circuit variables more specifically, are continuous values. So if you have a voltage, it can be anything or any value. But for the purpose of designing digital computers, we restrict ourselves to only discrete values of voltages. So either 0 or 5, for example. So this discipline helps us to have a simpler design procedure than analog circuits, and based on that we can build more sophisticated systems. That's why digital systems are able to basically replace analog systems. So examples include digital cameras, digital television, cell phones, CDs, etc. So having discipline or having restrictions when we do the design is not necessarily a bad thing. It has potential to even surpass using analog signals, for example, for the purpose of digital logic. What about the 3 Y's that I mentioned in the beginning of the lecture? Hierarchy, modularity, and regularity. So these are the design choices that we will follow in this course. So let's just go over their definitions. So hierarchy means that the system needs to be able to be divided into modules and submodules. So this is something that is understandable. So any complex system can be broken down into smaller subsystems or modules. As for the modularity, it is defined as having well-defined function and interfaces. So I think the concept is obvious from the definition that when we create these modules and submodules, the functionality of each one of them and the way that different modules can communicate with each other needs to be well defined. So if, for example, if we have a module that accepts its inputs in a specific form, the module before it that provides that data needs to know what is the appropriate form of the data that can provide to the module. And finally, we have the regularity, which is kind of intertwined with the previous concept as well. Encourages uniformity so modules can be easily reused. So for example, in a computer circuit, if a sub-circuit is bad, let's say if the wireless card is bad, you should be able to easily replace it with a new one, right? You shouldn't need to make any changes in the circuit of the computer, right? So that is the concept behind regularity. So in terms of digital abstraction, as I mentioned before, most physical variables are continuous. So examples include voltages on a wire, frequency of an oscillation, position of a mass. As for digital abstraction, we only consider discrete values. So I will go over in much more detail in later lectures about the concepts of digital abstraction. So one of the very first examples of a digital computer is the analytical engine. It is designed by Charles Babbage, and it is considered the first digital computer. So this computer was built from mechanical gears, where each gear represented a discrete value between 0 and 9. So as you can see, this computer was a decimal or base 10 computer, not necessarily a binary. So in computers that we use today, we have zeros and ones. This computer could cover, or saying it more accurately, it was based in 10, so the way that we count. Unfortunately, Babbage died before it was finished. As for the digital discipline, what we do is that we use binary values. So we use two discrete values. We either can have ones or zeros. One is usually considered as true or high value, and 0 is usually considered as false or low value. So ones and zeros are voltage levels in digital computers, but it can also be represented in rotating gears, fluid levels, etc. So digital circuits use voltage level to represent 1 and 0. Since we have two possible values, we call this system that uses discrete ones and zeros as a binary system, and any variable that can represent these two values is called a bit. So if we have one bit, we can show either a 0 or a 1. If we have 4 bits, we can show 16 possible combinations. I will go over these in more details at later lectures. So, assuming that we now understand what is a bit or what is a binary system, we need to come up with some sort of a mathematical way to be able to work with such a system. So that is something that was created or invented by George Boole. So he taught himself mathematics and joined the faculty of Queen's College in Ireland. He wrote the book An Investigation of the Laws of Thought, and he was the person who introduced binary variables. And at the same time, he introduced the three fundamental logic operations: and, or, and not. So these three fundamental logic operations, which I will go over them in later videos, are the building blocks of digital computers. So not only they provide a mathematical representation of the Boolean operations or Boolean algebra, they are very simple, right? So very simple to understand. So that is basically the same concept of discipline that I talked about, that we restrict our design choices, and then based on those smaller or restricted design choices, we are able to design more and more complex systems. So in this video, we talked briefly about some of the introductory concepts of fundamentals of digital logic. I don't expect you to understand everything that I discussed, but this should give you a good introduction to some of the basic definitions: abstraction, discipline, hierarchy, modularity, regularity. In later videos, I will go over the basic concepts and basic techniques that are used in digital logic design in much more detail. So in the same module, I have given you two external videos that I highly recommend you watch them and take notes of whatever new concept that you see in those videos, because by the end of this course you are able to understand all those new concepts, and you basically can design circuits that does the same thing as you will see in those videos.